Welcome back. In our previous lecture, we were discussing the principles of featurization. So, while discussing the principles of featurization, we talked about this compositional average features, which essentially you start with the elemental descriptors, elemental features, and you do a compositional averaging. And then we said that you might have certain situations where the interatomic interactions becomes very important. And so, when you deal with those type of problems, we discussed that there is a need to compute the interatomic interactions based on some sort of physical principles. And now there are different ways in this can be done. So one way of doing that is, of course, to do molecular dynamics or density functional theory calculations. But if the elemental compositions are complex, or if you do not have a priori information about the crystal structures, doing those type of calculations is going to be extremely difficult and time consuming. And therefore, what we do is we rely on semi-empirical thermodynamics. So more specifically, we will be using Miedema's semi-empirical model in order to come up with calculating the thermodynamic potentials like the formation enthalpy. So Miedema's model has a basic assumption. Miedema says that this is a macroscopic atom model. And basically what Miedema means by this is he's trying to approximate atoms by blocks. So let us actually go over the rationale of this type of approximation that Miedema has done. So once he approximate atoms by blocks, he says that the formation energies for forming a material by bringing these blocks of atoms together arises by elimination of discontinuities in the electron densities at the boundary of the Wigner-Seitz cell, as well as removal of the discontinuity of the electronegativity. So now let us actually unpack all of this a little carefully. So supposing here I am looking at a AB alloy, my A atom is a hexagonal black colored block and my B atom is a hexagonal white colored block. So if I am trying to make an alloy like this, what Miedema basically says is each of this block is the Wigner-Seitz cell for that particular element. And essentially, you are trying to model the interactions by bringing together blocks, and whatever changes are happening, you specify that they are happening at the boundaries of the Wigner-Seitz cell. Now, in some sense, this is not a very dramatically different approach from the traditional approach that materials physicists take, because in case of materials physics, basically what you are dealing with are the Brillouin zones, and the Brillouin zones happens to be the reciprocal lattice analog of the Wigner-Seitz cell. So how do you actually create a Wigner-Seitz cell, and what is this Wigner-Seitz cell? So this cell is basically a unique primitive unit cell for a given crystal structure, and you can construct the Wigner-Seitz cell by first considering a reference atom, let's say over here, and then what you do is you simply join this reference atom by straight lines to its nearest neighbors. So because 3D visualization is difficult, we are going to look at it from a 2D perspective, and then we will work through it. So after you have defined your reference atom, you will want to join them, the reference atom, with its neighbors. So we'll first start with the first nearest neighbor. So when we talk about the first nearest neighbor, you are basically looking at this atom, you are looking at the second atom, you are looking at this atom, and you are looking at this one. The other atoms, the ones at the corner, they form the second nearest neighbor and not the first nearest neighbor. So when we join the atoms, we first join the reference atom with its first nearest neighbors. After that, what we do is we take the bisectors of these lines. So for this atom on the left, the neighbor on the left and the reference atom, I joined it and then I drew the bisector in orange. Similarly, I start drawing bisector on the other side at the top and at the bottom. And once I have drawn the bisectors, I will see that there are certain points at which the bisectors are intersecting. So if I now consider the space, or in this case area, which is bound by the bisectors and the points of intersection of the bisectors, what I get is a Wigner-Seitz cell. So what that means is, if I have this type of a square, simple cubic type of lattice, the Wigner-Seitz cell, again, keep in mind that I'm looking at everything from a 2D perspective, the Wigner-Seitz cell of that also happens to be a Now, why is this actually important? So, this is important because if I consider any point which is inside this bounded region, that point is closer to the reference atom than any other atom. Similarly, if I now consider a point which is at the boundary, that point is equidistant from the reference atom and the neighboring atom. So, by using this Wigner-Seitz cell construction, what we have really done is, first of all, we have created a unit cell because the only atom inside this Wigner-Seitz region is the reference atom. That's the first thing. And the second thing is, we have now identified the space in which any point is closest to the reference atom, and the boundaries of that space, any point on that boundary is equidistant from the reference atom and its closest neighbor. So this has been an advantage of constructing the Wigner-Seitz cell. And because we are now specifying that all of the interactions are occurring only at the cell boundary, we need to concern ourselves with the electron densities and the electronegativity difference only at this cell boundaries. Now, depending on what type of nearest neighbors you have got, the shape of the Wigner-Seitz cell is also going to change. So, understand that this is very much a function of the crystal structure of the material. So, for instance, if I look at a slightly different geometry, so here basically what I've got is I've got my reference atom, and then you can think of all of these atoms lying on a circle. So basically I have got 8 nearest neighbors in this problem. So what I do, again repeating the steps, I will simply go ahead and join the reference atom with the nearest neighbors, and then after that I start constructing the bisectors. So the first set of bisectors I have constructed with the neighbors at the top, bottom, left and right, and the second set of bisectors I construct by looking at this neighboring atoms which are at an angle. So if I construct the bisectors from them in a slightly different color, this is basically what I get. And then if I consider the bounded region, what I essentially see is a geometrical figure which is four-sided. So I have got an octagonal type of Wigner-Seitz cell. So the significance of the Wigner-Seitz cell becomes very important when you try to understand the concept of equilibrium separation, because that is important when we try and understand the type of bonding which is taking place. So here, if I try and construct the alloy consisting of different elements, so in this case I have got a black element, a red element, and a blue element. So I'm trying to make a ternary alloy. And if the Wigner-Seitz cell of all of these elements now happen to be squares, then the alloy starts looking like this. So what you can see, this is basically a A4, B4, C type of alloy, where A and B are the black and the blue blocks, and C is the red block. If you have elements with different types of Wigner-Seitz cell, you can again do the construction similarly. So once again, I have got this black, blue, and red blocks. But now it turns out that I have got some spaces, and so this is not going to be a stable configuration, because as per definition, this entire thing is a solid, and if I'm breaking it down into Wigner-Seitz cell, I should be able to cover all of the space effectively. So here you will have a fourth type of atom, and so now you've got a quaternary alloy being depicted over here. So this is basically Miedema's idea when he tries to construct alloys by using the Wigner-Seitz cell of the constituent elements. Now what he further says is that you will be removing the discontinuities which arise at the boundaries of the Wigner-Seitz cell. Now why is that going to happen? Because over here, let's say your yellow is A atom, Wigner-Seitz cell of A atom, and the B or blue block is the Wigner-Seitz cell of the B atom. So A and B can have different electronegativities, and what we say is within the Wigner-Seitz cell, all the points are closer to the reference atom, and we sort of make an approximation that the electron density over here and the electronegativity over here is what it is. And similarly, you have a different value of the electron density or electronegativity throughout. And so right at this interface, you have a situation where the density of electrons is different and the electronegativity is different. Now, when you are forming an alloy, the elements are coming together, they're losing their individual properties, and they are essentially forming something which completely different properties. And so what that means is you can no longer allow A having its own electron density and B having its own electron density. It has to be smeared out. In other words, the discontinuity has to be removed. And that is basically what's happening with the electron density as well as the electronegativity. So this blue and yellow picture of your alloy then comes into this green picture where you are trying to have more or less homogeneous electron density and electronegativity. So then basically what Miedema says is that the energy which is expended when this type of thing happens is given by this delta H AB term, and he for good measure he is adding this IC which stands for interface, just trying to reinforce that this entire delta H is coming about by removal of the discontinuities at the interface. So what does this enthalpy actually mean? So it is dependent on the size of the individual elements or the size of the cell. It depends on the difference in the electronegativity and 1/3 power of the difference in the electron density. P and Q over here, these are fitting constants which Miedema found by looking at thousands of compounds and trying to fit this formula with thousands of compounds. And in the denominator again, it is what you have got is the average electron density of the two different elements. So this term is quite symmetric. This term is fairly symmetric. All of them are raised to the second power. And this term is again going to be symmetric. So what really matters is the volume of the two elements. So because the volume of A and B are different, the delta H AB interface is going to be different. So what this thing actually is nothing but an interaction parameter, which is what we had discussed when we were going over basic thermodynamics and we introduced the subregular solution formalism. So this is an interaction parameter in which you are putting an A atom in a matrix of B atom. You can simply compute delta H BA, and then this VA is going to change into VB, and now you just have the opposite case where you are putting a B atom in the matrix of A atom. So VA to the power 2/3, this term is actually correlating with the area of the Wigner-site cell over which this removal of discontinuity is occurring, and so that is why this term is appearing as a direct proportionality. The greater the area over which the discontinuity removal occurs, the larger the formation enthalpy or the interaction parameter term is going to be. So that's why VA to the power 2/3 appears as a direct correlation. This NWS to the power minus 1/3, this correlates with the average electron density at the boundary along a given direction, whereas this delta NWS 1/3 whole squared, which is what you see here in this last term, this correlates with the magnitude of the discontinuity. This is whole squared because this discontinuity is actually existing over an entire area. Similarly, this delta phi square, the term that you see over here, this correlates with the difference in electronegativity at the interface of the Wigner-site cell. And as I mentioned, P and Q are empirical constants. Okay. So once you have figured out the values of the interaction parameter, you will still need to compute the overall formation enthalpy. And so all of this is packaged together by using this formula. And I'm hoping that you'll be able to recognize which type of solution model we are talking about. And the answer to that, of course, is this is a subregular solution model. Just to refresh your memory, let me pull up the expression for the delta G. And here you will see that in the formation enthalpy part, we have got XA omega AB plus XP omega BA, where omega AB and omega BA, these are the interaction parameters. In case of Miedema's semi-empirical model, those omega AB and omega BA is nothing but delta H AB and delta H BA. There is a little bit subtle difference over here though. Instead of using the traditional values of composition, so XA, XB or CA, CB, we actually have these terms FAB and FBA. And this is because a little bit of sophistication that Miedema has actually introduced, because what he says is it's not just the different interactions when A is dissolved in B and B is dissolved in A, but also the extent to which A is surrounded by B and B is surrounded by A. And so that's why instead of using the simple composition, he uses this FAB and FBA type of value. And he also sets forward the methods for calculating the FAB and FBA type of value. So FAB and FBA is dependent on this term CSB and CSA. So these are what we call the surface concentration. I'll come to that in a minute. And then there is another parametric term over here called gamma. So gamma is 0 for solid solutions. Gamma is taken as 5 whenever you have short range ordering. So for instance, if you have liquids or gases, and if you have got long range ordering, as in case of intermetallic compounds, the value of gamma is taken as 8. Now, how do you actually get to this surface concentration? The surface concentration is essentially a composition weighting of the 2/3 power of the volume. So you can intuitively understand that because when you raise volume to the 2/3 power, you get something like a surface area. So basically what we are doing is we are simply taking this 2/3 power of volume, multiplying that with the composition of the element whose surface concentration we are trying to compute, and dividing that with the total of CaVA to the power 2/3. Okay, so once this part is done, then you can go ahead and calculate the formation enthalpy. Now it turns out that we are in luck because people have already evaluated the delta HAB value for different combinations of elements, and those tables are easily available. In fact, you can simply look at this book or in Miedema's 1983 CalFIRE paper, and you will find the delta HAB value already computed for you in the tables. So of course, when you write a simple Python code for calculating the formation enthalpy, you will need to calculate the CSA, CSB, FAB and FBA because these are going to be composition dependent. So depending on what compositions you're using, you compute them. After that, you plug in the values of delta HAB and delta HBA from the table. And after doing that, you are able to calculate the overall delta H for your alloy. So the delta HCH that we computed was the structural contribution to the formation enthalpy. Now what happens is, in addition to structural contribution, you can have other contributions to the formation enthalpy which can arise as a result of lattice strains. So in Miedema's approach, he tried to compute this lattice strain energy contribution by using a modification of Eshelby's model. So here the basic idea is you have got a regular lattice, and as long as you have got atoms, all of them of the same size, you do not really have a lattice strain. But supposing you now try to insert a larger atom in place of a smaller atom, your lattice starts barreling out like this, and as a result of that, you have got a certain amount of strain that is introduced, and associated with the strain there is going to be a strain energy. Now first approximation or first assumption over here is you are actually having a strain, but that strain is not enough to disrupt the bonds. Okay, so we can then think of this as a problem which lies within the elastic regime, and therefore you end up calculating this elastic strain energy using this formula. I'm not going to get into the derivation of the formula, that's not important for us right now. All you need to know is know this formula so that you can calculate the elastic strain energy. So basically, if you've got two types of atoms, I and J, the elastic strain energy is given by this expression. Mu over here is basically your shear modulus, V is the standard molar volume, and the K over here is the bulk modulus. So it turns out that in that same book by Hans Backer about Miedema's model, you will also get the values of bulk modulus and shear modulus, and you can directly pick up those values from these tables. Now the overall formation enthalpy is given as a sum of the delta H chemical, the delta H elastic, and the delta H structural. The delta H chemical is basically the delta HCH that we had computed earlier, and this is a part of your total formation enthalpy. The elastic formation enthalpy is what you are computing over here. Now, simply by looking at this nomenclature, you probably understand that we do the elastic strain energy calculation for Ij as well as Ji. So just like in case of the chemical energy, we had this interaction parameters, you can think of this is quite analogous to the standard thermodynamic subregular solution model, and you can think of computing your overall elastic strain energy by using the same subregular solution formalism. And so basically what you are going to do is you will start calculating delta H elastic as CACB, and here you will again have a CA times delta H AB elastic plus CB times delta H BA elastic. So this is your subregular type of formalism. The final component to the formation enthalpy is the structural enthalpy, and this is something which is associated with the change in crystal structure of the material. Usually the contribution of the structural enthalpy is quite small, so we are not really going to get down too much into it. So once you have calculated the formation enthalpy, you can then start using this as one of the calculated features in your machine learning model. It turns out that many of the problems that you will be dealing with will not be restricted to binary compounds. The formalisms we have discussed so far is applicable to the binary compounds, and we want to get into a situation where this type of calculations can be extended to ternary or multi-component systems. So for that, there are a couple of different ways of doing it. So the first one is Gallagher's approach, which is the one which is used very broadly, and this is essentially a very simple approach where the formation enthalpy of ABC alloy is simply taken as the sum of formation enthalpies of AB, BA and BC and CA. So one of the things I want you to understand is when we are using this type of approach, we are building up from the binaries. We are not breaking ABC into different binaries, but we are constructing ABC from different binaries. So for example, if you have a quaternary system ABCD, and if you are trying to, instead of building up from binaries, you are trying to breaking down, then what you will end up calculating is delta HAB, delta HAC, delta HAD. Then again you have got the delta H, so BC, delta HBD and delta HCD. So if you build up from binaries, this is what you will get. If you try to break it down from the quaternary system, then ABCD becomes ABC as one ternary, ABD as second ternary, ACD as third ternary, and BCD as the fourth ternary. And each of these ternaries is going to have three individual binaries, and so what will happen is if you try to break down from the multi-component system, you end up double counting the binaries, and therefore always build up from binaries, don't break it down from the ternaries. So this is one way in which you can extend it to multi-component system. There's another way which is based on minimization of energy, and here the idea is we start with an approach which is very similar to what Gallagher did. Only thing is we now say that the AB computed for a certain concentration of A, BC is computed for a certain concentration of B, CA is computed for a certain concentration of C, and those concentrations of A, B and C does not need to match the nominal composition. Similarly, phi 1, phi 2, phi 3 here are weights of this different ternaries, and so you can see that this is actually quite analogous to Gallagher's approach. Now, on top of this equation, we now impose conditions of mass balance. So the sum of the weights of the individual binaries equal to 1, and then the amount of A, amount of B and amount of C, when you extract it from this relation over here, should actually match with the nominal A, B and C considerations. So once this mass balance is imposed, essentially what you try to do is you try to vary the values of CA, CB and CC and find the minimum energy condition, and then that is supposed to be the structure. And again, the same thing can be done for the lattice strain energy, and you will end up with a fairly similar expression if you use Gallagher's type of approach, which will give you a relation like this. So this is the way in which you can actually extend this Miedema's and HLB type of calculation from binary system to multi-component system, and you can use this for creating the calculated features for the multi-component alloy systems that you are dealing with. Be advised, of course, that the accuracy of these models is not comparable to that of the DFT type of calculations, but then these are fast, these are structure agnostic, and therefore that makes them reasonably good candidates for using in this materials informatics type of approaches. Thank you for your attention.